Hi, this is my industry project, Depth Super Resolution for 3DGS face reconstruction. The input is a 256 by 256 8-bit depth map rendered by FaceLift, a single image 3D Gaussian Splatting method from ICCV 2025. The output is 1024 by 1024 16-bit depth. So the task is ×4 spatial upsampling plus bit depth recovery. Here are the training scripts, experiment notebooks, evaluation results, the upstream facelift code, and the paper figures. This function generates the training pairs. Line 30 reads the original 1024 by 1024 16-bit high-resolution depth map with CV2. Image read unchanged, so the precision is preserved. Lines 38 to 40 create the 16-bit low-resolution version. This is a pure spatial downsample to 256 by 256 using area interpolation. Lines 43 to 47 create the 8-bit low-resolution version. This step also quantizes the depth from 65,536 levels down to 256 levels. This simulates the information loss in low-quality depth output. The high-resolution target is 1024 by 1024, stored as 16-bit depth. The low-resolution input is 256 by 256, stored as 8-bit depth. That means 16 times fewer pixels and 256 times fewer depth levels. The model needs to recover both. This script generates binary face masks. The loss is only computed inside the face region because I do not want the model to waste capacity on the white background. Lines 57 to 58 compute each pixel's distance from white. The cropped face has a white background, so anything far from white is treated as foreground. Lines 67 to 72 use connected component analysis and keep only the largest region. Lines 75 to 79 use flood fill from the corner to close interior holes such as eye whites, teeth, and specular highlights. Around 72% of the image is white background. If I computed the loss on the whole image, the model would waste capacity learning useless pixels. Masking out the background focuses the training on the face region. The dataset loads triplets, low-resolution depth, high-resolution depth, and face mesh. It can also optionally load DSINE, pseudo-ground truth normals. Lines 106 to 111 use PIL instead of CV2 for loading. This is because CV2 on Windows caused heap fragmentation with 16-bit PNG files in long training loops. This was a real bug, and it took time to find. This is the model depth up res UNet. The base channel number is 32, so the encoder widths are 32, 64, 128, and 256. The bottleneck has 512 channels. The model has 7.77 million parameters. It uses a standard 4-level UNet encoder with convolution, batch normalization, ReLU blocks, and max pooling. The decoder uses transpose convolutions and skip connections. Now the most important part is the forward method. First, the 256 input is upsampled to 1024 by 1024 using bicubic interpolation. This bicubic image is already a very strong base prediction. Then the bicubic image goes through the full UNet encoder-decoder. The key design is the bounded residual. The UNet output goes through TNH, which is bounded between -1 and +1. Then it is multiplied by 0.5. So the residual is bounded between -0.5 and +0. 0.5. The final output equals the bicubic prediction plus this small residual clamped between 0 and 1. This means the network is not learning the full depth map from scratch. It only learns a small correction on top of bicubic. This design is important because bicubic is already nearly correct. It is about 99.8% correct. The residual learned by the UNet is less than 0.2%. But this tiny correction fixes geometric details at depth boundaries. In contrast, SwinIR tries to learn the full mapping without this residual prior and it collapses. Its L1 error is 37 times worse. Now I will explain the loss function. The first term is masked L1 loss. It measures the absolute depth error multiplied by the face mask, so the background contributes 0. The second term is gradient loss. It compares the spatial gradients between the prediction and the ground truth. This penalizes edge blurring. A gradient pixel is only valid if both neighboring pixels are inside the mask. The total loss is masked L1 plus 0.5 times gradient loss. I also tested an optional cosine normal loss. This compares predicted normals against DSINE pseudo ground truth normals. It uses a separate normal head so the gradient does not interfere with depth prediction. The 3D GS renderer produces normals with per-splat aliasing. This creates pits and bumps where splats disagree on surface orientation. This issue is also discussed in normal GS, 2D GS, sugar, and DN splatter. I spent 2 weeks trying bilateral filtering, but the problem was fundamentally unrecoverable. The validation L1 error plateaued at 0.0037, which was 59% worse than the baseline. So I used DSINE, a pre-trained monocular normal estimator from CVPR 2024. It takes the RGB image, resizes it to 480, runs inference, and produces clean normals. The output is then upsampled to 1024 by 1024, re-normalized to unit length and saved as an RGB PNG file. The result is clean normals with no splat artifacts. It processed 1,288 images in 3 minutes. Switching to DSINE at week 9 was the most important pivot in this project. Now I will show the results. First, this is the 5x5 cross degradation matrix. Each row is a model trained on one degradation type. Each column is a test set. The diagonal shows matched degradation with results between 40 and 46 dB, but the off-diagonal results drop sharply. The worst case shows a 13.5 dB gap between matched and mismatched degradation. This means a model trained on one degradation type can lose up to 13.5 dB when tested on another. This proves that 3DGS degradation is fundamentally different from standard bicubic degradation. Now, the most important result is mesh level geometric quality. The UNet F score is 0.999, which is nearly perfect. EDSR scores 0.637. SR ResNet scores 0.647. Both of these use pixel shuffle upsampling. That is a 35 percentage point gap. But if we look at PSNR, the picture is misleading. The UNet reaches 46.2 dB SR. ResNet reaches 46.5 dB, which is slightly higher. So SRRS net has better PSNR, but much worse mesh quality. This shows that pixel metrics can completely miss geometric damage. Pixel Shuffle redistributes depth values across a 4x4 grid at discontinuities. such as nostrils, lips, eyelids, and face boundaries. Pixel-wise, the values can still look close, but the final surface geometry is damaged. That is why mesh metrics such as F-score are essential for evaluating depth super resolution in 3D reconstruction. To summarize, there are 3 key findings. First, 3DGS rendering creates a distinct degradation setting. It includes splat boundaries, opacity falloff, and 8-bit quantization. This is different from the bicubic assumption in existing depth super resolution. The cross-test matrix confirms up to a 13.5 dB mismatch. Second, a simple UNet with a bicubic residual prior achieves an F-score of 0.999. Pixel shuffle architectures score only around 0.64, even though their PSNR can look competitive. This means pixel metrics are blind to geometric damage. Third, 3DGS normals are unusable because of per-splat aliasing. DSINE pseudo-ground truth normals provide a cleaner alternative. All code, scripts, and evaluation results are included in this repository. Thank you.